Hello, okay, we are back to the second clips, okay, talking about fast Fourier transform. Okay, from the previous clip, we already know the definition of Fourier transform, and this approximation is what we call discrete Fourier transform, and the computational issue that caused the slow processing, okay, as a quadratic function. And but the idea of way back in 1965 of what we call the Radix-2 of Boolean-Tukey's, okay, can help accelerate, okay, the speed of this DFT, okay, to into what we call the n log 2 of, okay, base 2 of n, okay, as n is a capital N is a number of data, okay, and so it's reducing from n times to just log n base 2, okay. And today we're gonna demonstrate that this type of algorithm is already available in many software, okay, and you can just call the object as a black box and run it, okay. But in some situation we still have to go back and use the basic idea to resolve some of the limitation of your computing problem, okay, which I will demonstrate it to you later. Okay, today we're gonna choose what we call it's a platform of I'm gonna don't save this first. Okay, we're gonna work on this file we call FFT Big Data, okay, which is available on this Google Share Drive, okay, of the Big Data MATLAB. Okay, here there's a Google Sheet file called FFT Big Data, which you can download and then put it in, change it to the format of the Excel here, okay. And also we're gonna have another file, so which is in here, Excel FFT 16384 so coming from solution, okay. I'm not sure we're gonna finish it in this clip or not, but we try, okay. But I already installed both the file here, okay. But we're gonna start here with FFT Big Data, okay, before, okay. Actually, there exists 3 sheets here, okay, that will demonstrate the idea of FFT algorithm, okay. But before we start that, let's get to know, okay, the objects that are available on the Excel platform that can help you to process computing fast Fourier transform, okay. This object is available in the data option here, okay, that available here, okay. It's a part of what we call in the object in data analysis. If you don't have data analysis appear in this option, it means that you need to install it, okay, by considering this option, okay, after you click the file option, you go to the add-in, okay, and you see here the Excel add-in here, press go, okay. This is the way that you can add many of the available object tools on the Microsoft Excel. Make sure that you add analysis toolpath. But if you want to write the program, the VBA program, using this tool altogether, you need to add analysis toolpath with VBA. Okay, you can see that I have a lot of available tools, okay, that working on the Excel format here. In this case, I already installed the analysis toolpath, okay, so just press OK. That's why I do have these options, okay, that are available here. So I'm gonna press here data analysis, okay. There's many tools available like ANOVA, statistic analysis, correlation, covariance, descriptive statistics, and exponential exporting. And also you have this one we call Fourier analysis here. This object is available for you to compute fast Fourier transform. Okay. First, before we look into anything else, we're gonna demonstrate you the ability to using Fourier analysis on Excel, okay, by considering this following example. Okay, let's start with, I'm going to create a new sheet here. We call sheet number 5, okay, sheet number 4, the new sheet down here. and then I'm gonna start, okay, make it a central, okay, and then I'm gonna count, okay, the number of data, okay, start with 1, okay, and then this one is the number is +1, okay, and we're gonna start with a small example first. Let's say we have 16 number, okay, and then I'm gonna put the boundary on this, okay, the border, and then this is your data. For example, this is your x sub t, okay, in terms of time domain, okay, this is your x sub t, x as a function of t, okay, as a time domain. This is a count of t also, okay, step by step, okay, the first data, second data. Actually, you need to multiply by the resolution delta, okay, if you go back to the notation of the Fourier transform, okay. But I'm gonna just, okay, maybe just randomly generate something down here. Just make sure there is a positive value, and then I'm gonna do tens time, okay, random, okay, and then I'm gonna do multiply by sign over 100, okay, times random, and then I'm gonna times, okay, the number d3 here, which is 1 here, okay, and then I'm gonna make round the number, okay, to have a 3-digit precision, okay, and this is just a, where I make a mistake here, okay, I need here, okay, put it here, okay, so this is the number, okay, so you can 3-digit, which means the third digit is 0. And then I'm going to go here, like here. And since it's a formula, it keeps changing every time you execute, okay? And so I'm going to make a copies, and then I'm going to put just erase all the formula here. So now it becomes the exact number. Okay, not going to change anymore because all the formula has been erased that related to the random. Okay, you might take a look at the, okay, I'm gonna look at the time series here. Okay, how it's gonna look like. Okay, so this is the number. Okay, it's gonna change. Okay, over here within this finite time horizon. Okay, it depends on, but we just discretize to only 16 number. Okay, and okay, I'm going to move it here. Okay, maybe we can erase it down. Okay. Next step is that if we want to compute x omega, okay, and you can understand that the discrete domain of omega also can be counted as 2 pi k, okay, divided by capital T, okay, and k can run from 1 to 16, the same as you discretize the times, okay, from 1 to 16, okay, but actually you have to start with 0 here. 1 refer to time 0, and 16 refer to 15 time delta, okay, and you know that after this the signal is vanished. Okay, if you want to find compute the fast Fourier transform here, okay, it's easy to just apply this, okay, the data analysis, and you can use the Fourier analysis here, and then they will ask you what is the input range. This is the input range, only 16. Okay, where is the output range? Okay, output range start, you want to say output range start here. Okay, start here. This is the x omega, and then I'm going to click OK. So once you put OK, this is the resulting of what we call the fast Fourier transform. So you can see that this one, the first number is the exact number, but this one, the remaining number become what we call, some of them are pure real number, but some of them are complex number. Okay, most of them are complex, and you can see the notation I here. I is a square root of -1. Okay, according to the formula. Okay. So you can see that it's very easy to use Excel, okay, to get the resulting of this fast Fourier transform. Okay, you guys might wonder that why people want to compute this complex number anyway. It's a part of the object in the Excel, so it need to have some specific application. Okay, believe me. But since this is a course of mathematics based, so I didn't talk. I will not spend time to talk about it that much. But the key thing that you want to find here is that you want to find the absolute, make this complex number in two terms. The first term is a magnitude value, which is we use the square root of the real part square, okay, plus the imaginary part square, then find the square root, okay, for each of these number. And then you get what we call the strength of the signal under the frequency domain. Okay, and that's in terms of interpretation is really valuable, okay, for just like I give you an example that you might wonder that why when you turn on the radio, okay, for a specific station, okay, broadcast or the bandwidth, like if you want your frequency modulation channel of or FM channel of 96.5, okay, megahertz, okay. Why when you turn on your radio to this range of specific frequency, you hear the signal of that station only. You don't hear the signal of the other station. Okay, that's the part of what we call the frequency domain here. Okay, it's very valuable when you study communication engineering, and also in the stock market also. Okay, when you want to know that the frequency of the selling and buying, okay, for a specific stock, okay, where is the bandwidth of the frequency of that frequency? You can't see it on the time domain, but you can see it on the frequency domain. And also you can detect some of the abnormal buying and selling signal, okay, which hard defined when you look at the time series, okay, here. Okay, so that's another course of mainly application of this technique, okay. But in this course, I'm going to give you just this example to show you that it's now very easy to compute this by using this Fourier analysis. But we're going to talk about the limitation of Fourier analysis here. Okay, there are two conditions of limitation of the Fourier analysis function now here when you want to compute the fast Fourier transform. Okay, but actually this number is I have to tell you that go back to the sheet here. It's a computation of this one. Okay, the x bar sub k here. But if you want the real value of x omega, okay, you need to multiply by the resolution of delta, where you discretize the continuous time domain to a discrete time domain. Okay, but in this you can see that when we analyze here, okay, we don't need to specify any delta. Okay, so once you know the data, the resolution of this discretization of this 16 number in time domain, you use delta multiply to each of these numbers, you get the real amount of the in terms of unit, okay, of frequency domain. Okay, let's go back to the limitation of the when you use these tools. Okay, when you use Fourier analysis here, okay, first of all, the restriction of the data is, okay, the number of data you need to analyze have to be in the form of 2 to the positive value. Like in this one, I'm using 16. Okay, 16 is what? 2 to the 4. Okay, 2 times 2 times 2 times 2. Okay, 2 times with 4 times. Okay, 2 to the 4. Okay, with exponent of 4. Okay, and actually you can use 8. Okay, the amount data 8. But if suppose I have only 10 number. Okay, suppose I only, you're not going to be able to run it. Okay, I'll show it to you that suppose that we do here. Okay, we do Fourier analysis here, and then suppose I change the time domain here. I change domain to only maybe 10 here. Okay, and then I click OK. They will say that Fourier analysis number of input must be a power of 2. For example, 2, 4, 8, 16. Yeah. And now you know why. Okay, you can know why. Why you have to be restricted to a power of 2. The counting in terms. You know from our last lecture that because of this, they implement what we call the Radix-2. Okay, they're going to separate it. You can see that once you separate it, if your n cannot be divided by 2, not become the integer value, you're not going to be able to decompose this. Okay, and if you keep decomposing this after term after term, okay, you have to make sure that the number of n is in the term of in the power, the counting of the total number of capital N has to be in the form of the power of 2 or the exponent of 2. The 2 exponent some integer value. Okay, that's the first restriction to use Fourier analysis. The second restriction is that how Fourier analysis is. You can see here in sheet 1 here. In sheet 1 that I already implement some example that I will illustrate to you that we have actually we are looking to solve this. Look at this sequence number in that shade, yellow shade here. Suppose this is the time domain. With the total number here, you're running down here. We have 8,191, but actually 8,192 because our count start from 0. And n is a counting start from 0. Like if I want to apply this, data analysis, Fourier analysis here, for sheet 1 here. Suppose I want to do this, on the start here, I put like this, and then we go down, just press column and then we go down because we don't want to drag it down. It was very long data. So this one is all 8,192. And then I was saying that so my output range got to be here. I want to find the Fourier analysis of all the data series in the shade yellow shaded area. Output range is here. I put the U here. And then I press OK. They will say here Fourier analysis, the number of input value must be 4,096 or less. So that's the problem of when you apply Fourier analysis here. To this type of problem then. So we go back here is that the sheet 5. So two restrictions when you using the Fourier analysis tool is that the first one is that the number of data must be in the counting of the total number of data must be in the power of 2. Some integer value as a power of 2. The second one is that how large power of 2 can go up to. It can go up to only 4,096. And 4,096 is in the power of 2 also if you really counting it out. But in this case we have the number of data larger than the power of 2, so we are not be able to run it. But actually we already find a result for you. How can we find this result for you? Why is it solvable in this case? We go back to what we do here. The solution is in this what you're seeing in the screen. We just apply the classical Radix-2 of Cooley and Tukey here. But before we extend to do for the case of 8,192, we start with a small scale problem first. Remember that the large scale problem is in this zone. This data range. But we start with a small one first. In this case, the first in this example, we only have, you can see here, only have 64 the data here. This is a different yellow shade area. Okay, the 8090 192 is in column S. Okay, but in column H, okay, there's only 64 based on this example. For example, I want to find, okay, actually this one is very easy if you want to find it, because in this one, okay, we do two way. Okay, the first one is in column I here. In the column I here, okay, actually is the direct use of the Fourier analysis. Okay, it's the direct use of the Fourier analysis. Okay, and maybe I show. It's very easy to do it. Just clear the content first. Okay, and then this is what I'll do. I'll just say that, okay, I'll do data analysis again, and then I'm going to perform Fourier analysis. Okay, and then this is a Fourier analysis that okay, this is a range of data, okay, that I use. Okay, and then what is the output range start? Where is the output range? Okay, the output range start here. Okay, start at, okay, here. Okay, so I just press OK. Going to take a while. They calculate. So this is the result. The same result as we already previously deleted. Okay. So this is the exact, because the number of data is only 64. So it's capable of using that Fourier analysis to compute. Okay. But remember that the algorithm behind Fourier analysis is also the fast Fourier transform. It's not the direct discrete Fourier transform. But you can see that there's some time of execution. It's not directly coming out. Even the size is only 64. Okay, when the size is only 64, it still take a while. Even when I think I got a pretty high speed computer down here. Okay. But you can look here that another solution in the green zone here, or the shaded green shaded here, actually is the same solution if you count the number one by one. Okay, and the magnitude down here, okay, is only is a command. Okay, a variable here. Okay, we call I is mean that imaginary. Okay, m is magnitude absolute. Actually, this command, okay, just find the square root of the real part square plus the imaginary part square. Okay, and that's one of the results that we normally look after transform this complex number to this magnitude, and then for different frequency range, okay, you can see the effects of the signal, okay, based on each bandwidth of frequency. Okay, and that's the main benefit of Fourier transform. Okay, you might see that when we talk about application of this tool, it's really coming out from the original of what you studied before about Fourier series. Okay, and at this point I still didn't explain to you the connection between Fourier transform and Fourier series. Actually, as from last time when we look at the original paper of Kurituki, you can say that they didn't mention anything about Fourier transform. They're talking about Fourier series. So is it the same thing? So is there any connection between that? Okay, we talk about it later, because if you can link Fourier transform to the Fourier series, okay, and Fourier series is in the general form of the solution of partial differential equation. That's another key application to find the linkage of this problem, okay, of Fourier transform, Fourier series, and general solution for partial differential equation. Okay, and that's the beauty of mathematics. Okay, it seems like one topic is independent to each other, but when as you go digging down deeper, you start to finding the linkage accidentally or unexpectedly. Okay, and then you can see that's we normally call this the beauty of mathematics. Okay, but this one we're going to explain to you where is this green zone coming from. Okay, the solution for green zone coming from here. Okay, is coming from we apply this Radix-2 fast Fourier transform. Okay, in this case our capital N is 16. Okay, we have 16 number here. So we're gonna separate, okay, the result in two ways. Okay, the first one we're gonna separate this summation to just the even order term, okay, and the ordered order term, okay, and this is what we did here. Okay, if you look at this, no, different file. Okay, the FFT big data here. Okay. Okay, to get the results of this green zone down here. Okay. Okay, let's consider here. Okay, now you have here. You understand where is this red zone, the yellow zone data coming from? Okay, from column H and column I, and then now we're gonna start to look at where is the column J coming from. First of all, okay, we're gonna separate this order 64 number or order term. Okay, we separate them into two groups. Okay, according to the Radix-2 formula here. This one here, you can see that N. This is the ordered order term. Okay, this and this is all. You use the command index. Okay, we index. Okay, the range of data here. Okay, and fix the address. Okay, and then the location. Okay, is according to the N here. When N is only the odd number. Okay, it will retrieve the data in this yellow zone just in the odd order. Okay, just here like 1 to 3. Okay, is what you see that this is from 1. Okay, this is from 3. Okay, 1, 3, 5. Okay, but actually in this odd value of N, it become no, this is odd value of N is the even order. You can see that this is the even order. Okay, because N start from 0. Okay, when N start from 0, this one when the order according to the N value is belong to the even order for the series. Okay, because N is a second number and N is equal 1 is belong to the order the second number, and then the 3 become to the fourth number. Okay, so this one you can see that 0.043 and 2.20. Okay, is being retrieved. Okay, and moved here by using the index function. Okay, here, and so on. The same as we're doing here. This is in the order number of N, but this one belong to the odd order of the series. Okay, again, you don't be confused. You might think that this is the even order. No, because N we start counting from 0. So when N start counting from 0, this one is belong to the odd order. Okay, because the 0 become the first number, the second one become the third number, the fourth become the fifth number. Okay, according to the sequence data down here. Okay, so now you have to know that when you study the linkage of this formula, you know where this coming from. Okay, first of all, we just add it up the N, keep this initial N, and then add it up twice. Okay, because the order moved to not in sequence, but just this is for the even order, and this one just for the odd order, according to this formula. This one. Okay, this one is summation of the even order, and this summation of the odd order. Okay, remember WK, we apply to use it later. Okay, so this one now you can just once you put it in here, you can make a copies. Okay, and according to this formula. So we already transformed this one and separate the data into two group. Okay, this one for the even order and this one in the odd order, and then this one, the xk here. Okay, and xk, actually this two is we apply Fourier analysis for only 32 data. Remember that we have 64. Okay, we have 64. Okay, but we separate the data to two groups, okay, and each group do have what 32, okay, each group have 32, and when we already separated this one, two group, the first group, the second group. So in this group 32 we perform FFT Fourier analysis for each of these summation. Okay, that's the result of this one. Okay, we do get this as a first group, okay, and this one we get for the second group, okay, and now we are ready now to apply this, okay, because for the whole group again, okay, we just use this term, okay, for the first 32, okay, of the results of x bar sub k, okay. We use this summation that consists of 32 data plus w to the k times the summation of this second group. Okay, so this is why we implement, go back here, the way that we implement down here, okay, the formula, all the formula here that get the results down here, okay. You can see that we need w to the k, okay. So we start to count the k, but remember that k down here in the Fourier transform here, k now reducing to 0, 1, 2, 3 up to n divided by 2 minus 1. So our original problem is that when n is 64, in this case k have to start from 0 to only 31 instead of 63, just like the original problem. So that's why we implement this, on the Excel format here. Okay, the k start from 0 and running until 31, okay, and then reset it, start at 0 again, and because when and finish at 31, okay. So this is how we set up the k. Why we need these two? Because you can see that the first one, k, start from k 0 to n, and then k plus n divided by 2, okay, is the summation again. So in this one we have this another k, okay, 0 from 31 again, but this one is k plus n divided by 2. It's the second half of the result. The first half just add it up, the second half is a minus, and we implement this formula, okay, on this the result here. Okay, once you already know the k value, okay, you know the w here, okay, w here, okay, here is a complex number of these two. Okay, look at the formula that we are using here. We're using the real part is sine 2 pi divided by 64. Why sine 2 pi? And this imaginary part is minus sine, okay, minus sine, but the real part is cos. Okay, cos of 2 pi divided by. Why we are using this? Because we go back to the original notation. Is that w is what? E to the minus I times 2 pi divided by n, which is in the polar form, and you know that this polar form can be expressed as cos of 2 pi divided by n minus I times sine of 2 pi divided by n. Okay, so this is the definition of w. So that's why we are doing this, okay. The real part is cos 2 pi, and we just approximate the pi as 3.1416 divided by n. You have 64, right? The number of data, okay, 64, 2. And this is the imaginary part, okay, here, sine 2 pi divided by n. Okay, but you need a minus sign here because the original notation you have minus I here. Okay, and then W is just a complex number of, you can see C1 is the real part, and C2 in the cell C2 is the imaginary part. So the way you can build a complex number using the Excel environment is that you use a complex C1, comma C2. C1 will become the real part and C2 will become the imaginary part. And that's how you set up the W value according to this formula. And then for the Radix-2 formula, you need WK, right? Running from K0 to N divided by 2 minus 1. And which is what we did here. When you know here, W, you start this with 1. Because W to the 0, okay, it's always 1. But this one is a C3, okay. but this one is you can use the IM product is what we call the complex number that we gonna use C3, okay, multiplied by F5, okay. So this one is this one multiply, okay, F5 is here, okay, F5 is here, okay, and C3. So this one become W squared. And then you move on to this cell, okay, you just make a copy until K is equal to 31. Okay, once you set up the formula here, the formula in this cell, you can just make a copy because it's keep moving down. And this one you can say that this is W squared, W to the 3 power of 3, okay, W to the 4th order, W fifth exponent of 5, and W exponent of 6, okay, and so on to 31 here. And then you can see that this one need to reset it again, okay. And to reset it is very easy. You can keep using it by applying the formula, but actually we just take a cell link, okay. You want to, with the Excel environment, it's very easy. Once you get here, you just either make a copy here or you just find a cell link here. Okay, it's linked to the location way back 32 location back, and then you get this W. That's handle what we call the W in this formula. W to the K to this formula. Remember the one is plus and minus, and then you're now ready to apply the formula of Radix-2 here. Okay, so now you know where the W to the K here, and then why every once it reach the half term is what they are looking for is what reset it again. Okay, and now you're ready to do this. Okay, because this one is only when you apply here. Okay, first of all, okay, it becomes the IM sum of what I71 and the IM product of F4. This is W to the K, right? You look at this formula, IM71, okay. Sum IM1 is IM is coming from imaginary, so they try to send this as a complex sum, okay. The sum of complex number using this command is the data in I71, okay, which is a complex number, okay. Plus here, okay, comma is a sum, is that you sum this to sum, okay. That's the product of complex number of F4, which is W to the 0, times the result from C71. C71 is resulting of it. You know the location of I71 and C71? Okay, I71 and C71. Okay. And then you see here, okay, this is I71, okay, here, and this is C71, okay, C71. So this one is according to the odd location, okay, and this one is belong to the even location, okay, according to the series, okay. But for the formula here, okay, here, okay, you can see that for the based on the formula here, okay, the summation here is belong to the odd location, even though n start from 0 to 4, but it belong to the odd location. The even location is here because this one belong to the second, fourth, fifth, and all. So once you know this, okay, you know this, you start from here. This is from I71, this one for the C71, okay, and then you apply using the Excel according to this formula. This one you just plus it together. This term, okay, remember that is in I71 plus W, okay, corresponding to the K, and this one is C71. Okay. The nice thing about this, once you be able to do this, okay, you can make a copy until you finish in this K to this one. You can once you get the results here, you make a copy, okay, until you reach the half of the series here. That's the result. But the second half you need to review it again because you have to make sure that this one, okay, IM product. I need glass here. Okay, you need to go back to I-71 and C-71 again. Okay, and now you can have W here. I think it's a little bit strange here. Okay. You can see that W to the K. Okay. So this one is become subtraction. Okay, you can see that. The first one we using a summation here. Okay, IM sum. Okay, the first part, because why? Because of this one. This one is plus. Okay, for the second part, okay, here once you go down here, okay, to this part, okay, you change the command. Okay, instead of you have IM sum become IM subtraction. It means that the first term minus the second term. Okay, the second term you need WK time. Okay, according to the same. Okay, so you just change this instead of IM sum become IM subtraction, and then you just make a copy out of it. Okay, so that finished this one. Okay, and you can see that the resulting from the green shaded area here is exactly the same as almost. Okay, and it might be deviate a little bit for when for the further down digit. Okay, that you can see, but the first couple of digits is exactly the same. Okay, why? Because we use approximation here. Okay, of 2 pi divided by n. Okay, that's caused some difference. Okay, and also there's some rounding error about the use of this approximation along the way. Okay, but mostly for the first couple of digits, 4 digit, I think is exactly the same. Okay, start changing from the 5th digit, I think 5th or 6th digit. Okay, but it's almost the same. Okay, and this is the way that, okay, you can see that we get the results here from in the green zone. Okay, by using what? Using this classical formula. Okay, and we only try to check it. Okay, we start with a small problem first here. Okay, and this is a small problem. Okay, only 64, so that we can apply the direct Fourier analysis to get the results first. Okay, and we can check that once we try to apply for a smaller scale problem, a half scale problem, and then we use the result from half scale to get the results from the full scale here. Okay, and let's go back to this problem again. Okay, the original problem here, we having what? 8,192 data, which we already show you that we cannot solve it using the Fourier analysis. Okay, but with this example, okay, if we separate this to two, half of them, 8,192 divided by 2 is 4,096, which is the maximum limit. You already showed before. I already showed you before that for Fourier analysis that can help you to compute. So you can apply this concept, this example of 64. Okay, I'm solving the case of 64 data by only solving 32 data each. Okay, and then combining these two data to get the result from the results of 64. Okay, and if we extend this idea, okay, we can use this to solve the same as we get this green area. But you can see now we don't have any comparison here with the exact direct use of Fourier analysis, because Fourier analysis is only be able to solve it only in case of 4096 as a maximum value. Okay, so okay, I think that I'm going to stop here. Okay, for this this example. Okay, for you to understand that we can apply the Radix-2 here formula. Okay, to solve this problem. Okay, next time we will explain to you in more detail about how this 8192 can be found, which I think you already see. You should be able to see it, that, and we implement it in sheet 2 and sheet 3. Okay, we explain you in sheet 2. Okay, sorry, we explain the result in sheet 2. Okay, and then you know that in sorry, I make a big mistake. Okay, the result is in, I believe is in sheet in this sheet. The result is already available in this sheet 1, and then in sheet 2 here is we're gonna extend to use instead of we doing Radix-2. Okay, we can extend this idea to what we call the Radix R. And R can be 3, 4, 5, 6, 7. Okay, and in this case we are using what we call the Radix R, and I think that I have some other file we call Radix-3 FFT. Okay, down here in Google Sheet. So this is the formula for Radix-3, and we also can extend to Radix-4, Radix-5, or whatever. But in general form is coming from this extension of Radix R. Okay, and our Excel, okay, in the second sheet here is a demonstration of the Radix-3. Okay, for a very small problem where we 48. Okay, we're gonna explain to you in the next script. Okay, so I think that from this part, okay, I'm gonna stop here and then let you repeat, go back and rewatch it in many detail that you might not be able to follow. Okay, my explanation in real time. Okay, see you in the next script.